We are at the bottom of page 6. Displacement distance graph for transverse waves. If a transverse wave travels in a medium and the photo is taken from the side, the photo will show the displacement of all the particles from their rest position at the instant the photo is taken. This is called a displacement distance or displacement position graph. The displacement means the distance moved by the particles in a given direction, which in our case is either upward or downwards. If we were to look at this diagram, this is showing us a wave passing through a number of particles. Okay, so we can see the particles over here in green, and although their rest position is the line in the middle here, as we can see from the note over here, but since the wave is passing through them, they have moved either up or down depending on where the wave is. As a bit of a reminder, we have that the wavelength is the distance between two successive similar points. In this case, we have two crests to measure the wavelength lambda, and the amplitude is the maximum distance that the particles are moving away from their rest position, either upwards or downwards, as the note is saying. So normally all the particles would be at their mean position, but as the wave moves through them, they get moved. We're going to view a couple of animations to help us understand this principle. Okay, so what we have here is an animation showing us a sort of droplet of water falling in a pond or a container, a large container of water, and we have the particles of water mapped throughout the diagram, marked with white dots. Okay, so as the water droplet falls, it will cause the central dots to move down and then back up and then back to the middle, back to the rest position. Okay, and the wave moves outwards. But as we can see, the particles only move up and down. Okay, they don't go, so the middle particle, the one that is being hit, is not ending up to the side. It is simply moving up and down. Here we have an example of a transverse wave being created with a slinky. Once again, as we can see, the hand on the left is moving the slinky up and down. And we can see that the coils, one after the other, move up and down while the wave, meaning the energy, is being transferred from left to right. Also, we can notice that the hand on the left is creating two waves. The first one a bit slower and the second one a bit faster. And as we can see, the first one has a much larger wavelength than the second one. Then if it has a larger wavelength, it would have a lower frequency. If it has a smaller wavelength, then it would have a higher frequency. Now the animation we are seeing now is a bit more accurate to what actually happens in real life. This is showing us what we call a cross-section through something similar to a water wave. So we can consider this to be the sea creating waves and going from left to right. We can follow the wave going from left to right. Now the animation is marking out positions of water particles throughout the body of water, throughout the sea. And to help us understand what the movements are, there are two that have been marked in orange. Okay, we have one closer to the top, and we can see that as the wave passes through it, it goes up and down, but it also goes slightly to the right and slightly to the left, creating a bit of an ellipse. Okay, the movement is not a perfect straight line, it is a bit of an ellipse. And further down, the same thing. Okay, so the closer to the surface a particle of water is, the larger the movement. As you can see, the ellipse at the top is much larger than the ellipse at the bottom. Incidentally, and that although the particle at the top is going in an anti-clockwise motion, the particle at the bottom is following a clockwise motion around its ellipse, around its movement. Now you might have experienced this when you are swimming in the sea. If you are swimming in the sea and the waves are rather strong, you might have noticed the sensation that although the waves might push you closer to the shore, but there might be times where you feel that the waves are pulling you outwards. So they push you inwards, but then they might pull you back out. In fact, whenever there is a large tsunami happening, one of the first things that happens to beaches is that a lot of the water is pulled outwards. And that is one of the first signals that a tsunami is about to happen, because the water pulls itself outwards and the level of the sea drops considerably. However, there isn't always enough time for people to react to protect their belongings, their houses, their cars, etc., which is why tsunamis cause a lot of damage. Moving on to the top of page 7. And once again, this diagram is showing us the same thing we've noticed, the same thing we've talked about. So in this case, the wave is moving from left to right. That movement of going from left to right is called the propagation. It's a bit of a technical term, but you should know it, okay? So the propagation of a wave means that it is moving in a particular direction. So if I say there was a disturbance on the left and the wave propagated to the right, that means that the wave was created on the left and it moved towards the right. The wave's energy moved towards the right, not necessarily the particles, because as we said, the particles move up and down, or they might move in a bit of an ellipse, but generally they move up and down. In this case, the wavelength is being measured from two troughs rather than two crests, but it doesn't make a difference. Now, I'm going to link the video mentioned at the bottom so that you can find it much easier through the assignment on Teams. This video is a general overview of what waves are. As something interesting for you to try, I would like you to visit the other link I'm going to add, which is that of a FET simulation. I've used these in class before, okay, and this is going to let you experiment as if you had all the tools available. Now you can try some of these things if you have a rope, or if you do have a slinky, you can try these out at home. But since not everyone has these, you can use this simulator. Okay, so this simulator has a number of functions. So what we are seeing now is basically, it is showing a sort of spring or a rope, okay? And you can control the left-hand side of it. You can control the wrench over here. So if it is set to manual, then you will be the one controlling the wave, like so. So if I click on the wrench and I move it up and down, I can create my wave. Okay? There is no need to move it in a particular way. You can even zigzag and, go up and down extremely far or extremely close. It will still propagate, so that we practice the term, it will still propagate to the right. Something else you can do, instead of moving it manually, you can use what is called an oscillator, okay, which is basically, it is mimicking if the spring or the rope were tied to a motor. Okay, so you can change the amplitude from the bottom. Okay, so the smaller the amplitude, the less far away it's going to go from the mean position. And if you were to change the frequency, then the wave will go up and down a bit faster. Okay? Now, something that we haven't talked about is what damping is. Now, damping is a bit of an advanced principle, but basically, the more damping you have, it would mean that all of the movement, all of the input movement in the wave is going to be absorbed within the wave. As we can see, nothing is reaching the right side with lots of damping. With no damping, none of the energy is absorbed. So it will be like the wave will go on forever. Alright, so let's add a bit of damping to calm it down. Finally, there is also the option to have a pulse. So what is a pulse? So basically what you do is you click it once and it will send one complete wave, and that's it. You can change the amplitude, you can change the pulse width. Okay, so you click it, you just click the green dot, and it will send one wave. The shorter the pulse width, in this case the pulse width is acting like the wavelength. So the shorter the pulse width, the higher the frequency it gets. Okay, you can even click it consecutively and you'll get even more waves. So you can also experiment with these options with the damping, even though we won't be going into what damping is. You can experiment with the tension. Something else that you can change is what is happening on the right hand side. So right now I have a loose end, which is a ring going up and down this pole, this shaft. Okay, if I select a fixed end, then the end will not be moving. So when I send a pulse, okay, it will reach the right hand side, and since that is fixed, the energy will be bounced back, will be reflected back. We will be talking about reflection at a later stage. So I can have a fixed end, I can have no end at all, which means that the wave will not have a limit, so it will pass through and will keep on going outwards. We have this image of a window here. I want you to give it a go, try it out. Alright, try the different functions. You can even sort of use this reference line to see the amplitude. You can use a timer. Alright, there are different things you can do. Since we're not in class and we can't go to the lab and you can't experiment with things hands-on, you can at least use this.